All right, everybody, here's our video on universal gravitation and Hooke's law. Okay, so universal gravitation. There is on your equation sheet, and I'll let you hunt around and find this on your equation sheet. There's an equation for the force of gravity um, in situations that is not just on Earth's surface. All right, so far we have looked at the force of gravity as it relates to the surface of the Earth and something that is on Earth's surface. Force of gravity is equal to mass times g, where g is the acceleration of gravity. However, what if we want to calculate the force of gravity between things that is not the Earth and something on its surface? There's a way that we can do this. And this becomes a separate equation. So when I do this, I'm going to write Earth's surface. So anything that's sitting on Earth's surface, we can do this because g is the acceleration of gravity on the surface of the Earth. If we instead, though, if we want to do the force of gravity acting between any two objects, no matter how far apart they are, no matter what size they are, that gives us an equation g, capital G, times m1 times m2 over r squared. Now, this capital G is a constant. This is what you can see down here, this capital G constant. It is 6.67 times 10 to the minus 11th. And then it's got weird units on it, Newton meter squared per kilogram squared. You don't have to remember those units. They're given to you. So G is this constant. This capital G is this constant. Mass 1 is m1, so the mass of one object we're looking at. Mass 2 is m2, the mass of whatever the other object is that we're looking at. And then r is the distance between the centers of those objects. So here we have G is this. I'll just write them down. M1, mass of object 1. Mass of object 1. M2 would similarly then be the mass of object 2. The mass of object 2. And then R is the distance between the centers of the objects. The distance between the centers of the objects. Okay. Distance between the centers of objects 1 and 2. All right, so if we have all these variables now, we can figure this out, right? And these objects, we didn't specify what they are or how large the objects are. We just know that they are things with mass. So any two objects, they could be particles floating around in space. They could be the sun and the earth. They could be the earth and the moon. They could be you and your crush, right? You and your crush gravitationally attract each other. You both have mass. You could calculate the force of gravity that is pulling you to your crush and similarly is pulling your crush to you. All right. So we have this equation. The force of gravity between any two objects is g m1 m2 over r squared. Now that is on your equation sheet. I'll let you go find that on your equation sheet. So you never have to remember that, never have to memorize it. Okay. Let's take a look at some practice problems here. First problem, what is the force of gravity between the sun and the earth? All right, so I give you the mass of the sun and the mass of the earth and the radius from the sun to the earth. All right, let's try this out then. Okay, so the force of gravity is g m1 m2 over r squared. Okay, so excuse me, if we take a look at these, right, let's plug in some numbers. So g, this gravitation constant, 6.67 times 10 to the negative 11 is g. Mass of m1, 2 times 10 to the 30th kilograms, right? That's the sun, mass of M2. And now we're looking at what does the sun also have a gravitational force with? It's the Earth. So 6 times 10 to the 24th kilograms. And then that is divided by r squared. So r, at the distance between the centers, we have 1.5 times 10 to the 11th meters. 1.5 times 10 to the 11th meters, and it's r squared. Don't forget that squared. Okay, so now we have all the numbers plugged in. All we have to do is stick them into the calculator. Here, though, is your reminder for scientific notation, right? That's the times 10 to the stuff. Scientific notation in the calculator. So over here, I have just a picture of a TI-84, just an image that I got from Google. If I want to type the number 6.67 times 10 to the negative 11th, remember, we don't type this whole times 10 to the stuff. We do something a little easier. That something a little easier involves this button. That's not a fine enough highlighter right there. It involves that button with the EE right here, right above the comma. So it'd be second, comma would get you to that EE. That means times 10 to the. So we would type in, and this is how you would see it show up in your calculator, 6.67, right? Hopefully you know how to type that, 6.67. And then times 10 to the would be second, comma, and that would show up on your calculator as a small capital E. Times 10 to the negative, remember to use the negative sign and not the minus sign. So E negative 11. 6.67 E minus 11. So E just means times 10 to the, and then we have the negative 11th power. Now we have some other numbers in here, right? 2 times 10 to the 30th. If we want to type in 2 times 10 to the 30th, we would type in 2 and then times 10 to the, remember, second, comma, gets us this EE, this capital double E, but on the screen it only shows up as a single double E, or a single capital E, so 2E30 would be that one. 2E30. If we want to go to the mass of the Earth, right, 6 times 10 to the 24, 6E24. And finally, 1.5 times 10 to the 11th, 1.5 E11. What's nice is if we are going to type these all in, all right, if we're just going to type these all in, we could, I'll clear this out for just a moment. All right, so I want GMM over R squared, right? G, mass sun, mass Earth, over the radius between them squared. I want 6.67 E minus 11, negative 11, sorry, times, right, the times key, mass of the sun, 2E30, times mass of the Earth, if I can remember mass of the Earth, 6E24, times, and I'm running out of space, so I'm going to go on to the next row, time, oh, I'm sorry, this is not times, because that's GMM. Now we need divided by R squared, so divided by R squared. What's nice is in scientific notation, when we use the E's, it automatically just knows that that is one single number. So since our radius is 1.5 times 10 to the 11th, I can just do divided by 1.5 E11. And since radius gets squared, then I can just hit the squared key, right? Just the squared over on this left side here. And then you hit enter equals, and it will pop out a number. I'll get my actual functioning calculator here. Times 2E30 times 6E24 divided by the radius squared. And I get my result. It popped out 3.56 E22 is what my calculator spat out. All right, so if we're going to look at that in the context of this problem, right, that means 3.56, and that capital E means times 10 to the, and then it said 22, so times 10 to the 22nd power. All right, remember this is a force. What units does force get? Newtons. So there's our answer. Times 10 to the 22nd newtons. That is a whole heck of a lot of force. My gosh. But I suppose it does have to make the Earth quite literally go round. So it does have to be a lot of force. Okay. As a quick note, that's not just the force of gravity that the sun exerts on the Earth. Right? This force of gravity, if I switched these two masses, if I instead looked at the force of gravity that the Earth had on the sun, it would be the same number, right? Because multiplication, we could do m1 times m2, which would be the exact same thing as m2 times m1. So this is a great way for us to see Newton's third law in action. So we can actively see that Newton's third law is applying here, right? The force of gravity that sun exerts on Earth is the exact same as the force of gravity that Earth exerts on sun, which we can then take back to this force of gravity as mg that we know and have used several times, right? When we are standing on the Earth exerts force of gravity down on us. All right, if we are to be standing on Earth exerts force of gravity down on us. So here's our free body diagram for me, the person. Force of gravity, and then there's a normal force back up. But if I were to look at the FBD for the Earth, right, the Earth is pulling me down with gravity. So for Newton's third law, I am pulling the Earth up with gravity. And it's the exact same force. These two forces have the same magnitude because we just calculate it with GMM over R squared. We just know a good chunk of these variables when we're on the surface of the Earth, is why we can simplify it to mg. But on the Earth, right, I pull Earth up with gravity, and then I push Earth down with normal force, right? That's the contact between my feet and the Earth. That's the normal force right there. So that's how Newton's third law can be seen pretty easily in this universal gravitation, right? Whenever one thing exerts gravity on another, the second thing exerts gravity back on the first. Okay, number 2, it asks, what is the acceleration of the Earth due to this force? Now remember, how do we relate forces and acceleration? The sum of the forces is equal to mass times acceleration. And in this case, the only force acting on the Earth is the force of gravity due to the sun. Well, we know the mass of the Earth. Mass of the Earth is 6 times 10 to the 24. And that's kind of my cheater notation, and I'll write it a little neater. 6 times 10 to the 24 is the mass of the Earth. I just kind of write it in calculator notation because it's faster to write a capital E instead of times 10 to the. So 6e24 times our acceleration is what we're looking for. And then we know the force of gravity on the sun, or the force of gravity from the sun to the Earth, 3.56 times 10 to the 22nd newtons. Okay, divide both sides by 6 times 10 to the 24. 3.57 E22 divided by 6 E24. I get 0.00595. It's acceleration, meters per second squared. All right. There's our acceleration of the Earth due to the force of gravity between the Earth and the sun. That's not very much, right? That's why it takes us 365 days to go around the sun, is because this is not a really large acceleration. It doesn't make the Earth go around very quickly. All right, moving on. What is the acceleration of the sun due to this force? Okay, so here we're looking at a similar thing, right? This is what we were talking about with Newton's third law. We just looked at the Earth. Now let's look at the sun. So the sum of the forces on the sun is the mass of the sun times its acceleration, force of gravity, and this time it's what's exerted by the Earth. All right, so mass of the sun, we can look up above. We get 2 times 10 to the 30th. So 2e30 times its acceleration of the sun. Is equal to that force of gravity between the sun and the earth, which, remember, those are equal to each other. So 3.56 times 10 to the 22nd power. All right, then divide by 2e30. So acceleration of the sun due to the force from the earth is, I get 1.79, and my calculator says -8. But here's the thing with AP notation, and this is what's kind of dumb. You can't write E notation for AP. You have to write it as times 10 to the notation. So times 10 to the -8. I don't fully understand why AP does it. It means the exact same thing, but that's just a thing that they do. So our answers always have to be in times 10 to the notation. So 1.79 times 10 to the -8 acceleration meters per second squared. All right. Moving on. Elliptical orbit of Nereid, the third largest moon of Neptune, is very elliptical. It gets as close to Neptune as 1.38 times 10 to the ninth, and as far away as 9.36 times 10 to the ninth meters. That's actually kind of a weird thing, right? Because if we look at, right, say that's Neptune, its moon is going to orbit around it kind of like this, which is weird to think about. A little weird to think about, but right, this is its closest point, and then this is its furthest point. I don't know why I did a wavy line, but that's its furthest point right there. So it's going to be a lot closer over on this side than it is over here. And this tells you exactly exactly how much that is. All right, so we're asked how many times bigger is the force of gravity when Nereid is closest to Neptune than when it is at its furthest? All right, let's try this out. So we're asked to relate force of gravity at its closest and force of gravity at its furthest. So let's find both of those. Force of gravity when it's close, right? G m1 m2 over r squared, but this is r when it's close. Then we're going to have to also find force of gravity when it's far. So G m1 m2 over radius squared when it's far. All right, let's plug in some numbers. So force of gravity when it's close, 6.67 times 10 to the -11, right? That's a G, our constant. And you never have to memorize it. I just have used it so many times that I haven't memorized. Mass of Nereid, 3.1 times 10 to the 19th. Mass of Neptune, 1 times 10 to the 26th. All right, and then divided by r squared. Radius when it's close. I said as close as this and as far as this, so we'll take the close one. 1.38 times 10 to the 9th, and that gets squared. All right, so let's plug this into our calculator. 6.67 e minus 11 times 3.1 e 19 times 1 e 26 divided by 1.38 e9 squared. And I get 1.05 times 10 to the, or e, but this is an answer, so times 10 to the 19th. We have to use that times 10 to the notation. All right, so there's our force of gravity when it is close. Force of gravity when it's close. What about force of gravity when it is far? Well, we plug in a lot of the exact same stuff. Our constant, G, is still 6.67 times 10 to the -11, -11. The mass of Nereid is still the same, so 3.1 times 10 to the 19. The mass of Neptune is still the same, 1 times 10 to the 26th. Well, only thing that's changed now is how far away it is. Now, when Nereid is at its furthest, they have 9.63 times 10 to the 9th. meters between them. Don't forget r squared. All right, so the force of gravity when it is far, if we plug this all into our calculator, we get 2.16 times 10 to the 17th. 2.16 times 10 to the 17th. It's a force newtons. Okay, so you can actually see a lot here, right? This is 1 times 10 to the 19th. This is 2 times 10 to the 17th. So if we're looking how many times bigger is this force of gravity, we're going to take force of gravity when it's close and just divide it by force of gravity when it's far. That'll tell us how many times bigger it is. All right, so force of gravity when it's close, we get, that was 1.05 times 10 to the 19. Force of gravity when it's far, 2.16 times 10 to the 17. So it is, if I plug this into my calculator, 10 to the 19 divided by 2.16 times 10 to the 17, I get 48.6 times bigger. That is astonishing. All right, the force of gravity changes that much as the moon goes around Neptune, and that's a real number. That is a true number, which is just kind of awesome to me. I love space. It's amazing, all the things that we can get. But the force of gravity changes by almost 50 times its own value. All right. That's I'll pause the video here just so it's kind of broken up into two. That is universal gravitation. Next video to follow along, we'll say more about Hooke's law. So that's it for this video. Let me know if you have any questions.